The ideas of convergence and continuity that we know from calculus are useful in more general contexts. The basic idea is that in order to talk about convergence, we need to find some way of saying when two things are close, okay? And that is what the metric space is all about. A metric space is something in which this notion of distance makes sense, okay? So let's be more precise here, and let's start with the definition. Okay, what is a distance? Let's say we have a set X, okay, whose elements we call points. And we will say that X is a metric space if for any 2 points PQ in X, we can associate the distance, a number. We can associate a number dpq, which is the distance between P and Q. Okay, and this distance has to satisfy three properties. Okay, so this is metric space, distance. So the distance function has to satisfy property A, the distance must be always positive. Okay, as long as the 2 points are separate. They are not the same point, okay? Of course, the distance from a point to itself must be 0. The second, it's that the distance from P to Q it's a symmetry property. It's the same as the distance from Q to P. Okay, and then the third one is the triangle inequality. That the distance from P to Q, if we go in a straight line, is less or equal than the distance if we stop somewhere else before. Okay, so the distance from P to R plus the distance from R to Q. And this is for any R in X. Okay, so these are the three properties that define a distance. Okay, and these are, of course, we know that these properties hold for, well, for the notions of distance that we are used to, right? But the point here is that these apply to more general contexts. So for example, let's see some examples. Examples. Example number 1. So this is the prototype, okay? In this case, the set X is the real numbers, okay? And the function that gives the distance is the absolute value of the difference between the two real numbers. Okay, if you want to draw a picture, so we can have P and Q, Q on the left, and the distance would be the segment between them, but we take the absolute value because Q could be on the left of P, okay, and in that case P minus Q would be negative, but we want a positive distance, okay? This is what we call the usual metric in R. Now, this is the line. Then we have the complex numbers, right? When X is the complex numbers. There we go. In this case, the distance is the modulus of P minus Q, okay? Notice it looks the same, but it's not the same. Before we have the absolute value, now we have the modulus. Remember, the modulus in the complex numbers is the product of the number times its conjugate, okay? And if we want, we can write it, sorry, with the square root. Okay, now it's good. This defines the notion of distance. Okay, in this case, we have our P here, our Q here, and what we are actually measuring is the distance, the length of the segment that connects the two points. Okay, we can do that also if instead of the complex structure, we take R2, that it's also the plane, but the structure is different. Okay, C is a field, R2 is a vector space. So in this case, we have the square root of P1 minus Q1 square plus P2 minus Q2 square. And this is the length of the vector PQ, okay, as we learned in linear algebra. Okay. So that's also, it's a geometrically, it's the same notion of distance as we had before. It's just the length of the segment that connects P and Q. Okay, but we could do other examples. We could still think about R2 and define the distance in a different way. There is this one called the taxi cab distance, taxi cab metric. Okay, it's called the taxi cab metric because it's like in a city that you have your buildings, right? And then to go from one point to another, from point P to point Q, then the way you measure the distance is in blocks, right? So you need to, you don't go straight because you cannot cut through buildings. You need to follow the streets, the grid. Okay, so how do we define the taxi cab metric? It's we call it D1 to this one, and this is D1 between P and Q. This is going to be P1 minus Q1 in absolute value plus P2 minus Q2 in absolute value. Okay. We have also, we could still be thinking about the plane and do a different type of metric that is called the supremum metric. Okay, the supremum metric, we call it D infinity, PQ. Okay, and this is the maximum between P1 minus Q1 in absolute value and P2 minus Q2 in absolute value. In this case, the distance between 2 points, we have our P and our Q, is going to be the maximum between these two quantities. This here is P1 minus Q1. And then we have the vertical one, that is P2 minus Q2. So we will take always the maximum. Okay. These are all examples of metrics. Okay, and the space is the same, R2, the plane, but because the metric is different, the properties are different. Okay. And in all these cases, we can check the properties of metric. It's only the only one that is always a little trickier is the triangle inequality.